The following was made as a television videotape. Its purpose is to provide orientation for those teaching the Chem Study course.
Any teacher who is trying to do a good job at his course is continually revising it. Each year it's a little bit different from what it was in the past. The pressure to revise has in the last dozen years or so been greatly increased, largely due to the summer programs of things like the National Science Foundation, where a teacher goes back to school and finds out what's going on now in his field. In chemistry, the program in the high schools has been greatly benefited recently by programs supported by the National Science Foundation. One such program is the Chem Study program. Here are some films, there are 25 altogether, which have been made by Chem Study for use in high school work. Here is a guide that goes with the films. There is a teacher's guide to accompany the text for the student, of which this is a copy. And most important in many ways, the laboratory manual for student use in the experimentally based part of the course. There is also a series of standardized examinations to see how the students are proceeding with these ideas. Chem Study got started about 5 years ago. It was based on the idea that teachers would like to try something different than what they now had available to them. It was based really on teacher discontent. About a dozen outstanding university and college professors got together with about a dozen very outstanding high school teachers. Their first decision was to see what should be done at the high school level. What would it be nice if the students could understand? What would it most profit the student if he could see and understand in chemistry? It was decided to leave the question of whether the student really could do this to the student. Write something and then try it out. In the course of the 5-year program, some 400,000 American students have used Chem Study materials. We think the evidence is overwhelming that this kind of approach can indeed be successfully accomplished by the American students in typical American high schools. The course is not gauged just at an elite group. We designed it for any student who wished to take chemistry. And the evidence is quite large that not only can the good students do well in this course, but so can those who are much less gifted. Now, what actually goes on? What is it that we tried to do? Well, perhaps one of the most important emphases was to put the student in the laboratory and have him do an actual experiment. Have him study a system that he had never seen before, that had not been discussed in class. Do the laboratory on his own, and on the basis of the observations he had made, then go into the classroom and with his classmates discuss what he had observed. Put the observations together and come out with some ideas, some concepts, some models which would be modern in scope, which would agree with the kind of things a chemist, a practicing chemist, thinks about. Not because the student is to become a chemist, but because he is studying chemistry. Now, the key to this is the teacher. Thousands of people have worked on Chem Study trying to prepare things that the teachers would enjoy and would find profitable. One of the men who has done a great deal is Professor George C. Pimentel of the Department of Chemistry at the University of California in Berkeley. He was editor of the text and in general charge of producing all of the printed materials. Professor Pimentel.
Thank you, Art. In this lecture series, we would like to take up the major subjects that come up in the Chem Study course and discuss with you why they are presented as they are. Many subjects will be presented in slightly different ways than you're used to. Some new subjects will come up. And we hope to be able to discuss this with you and give you a feeling for why it was done as it is. And no subject is more important and came in for more discussion than the question of the introduction of the atomic theory. We wish to begin the course introducing the atomic theory. It's the cornerstone of chemistry today. On the other hand, we wish to initiate the course with a strong experimental flavor. We wish the student to have the opportunity to draw the principle, in this case the atomic theory, directly from laboratory experience that gave him a clear feeling for the logic. Now, you understand the problem we faced. The student comes to the classroom these days, as you well know, believing in the atomic theory. He gets this in junior high school, he gets this in the funny papers. He already believes in the atomic theory. Our problem is to have him wonder why he believes in it. We decided that there were a variety of ways in which the atomic theory could be introduced. Let me put some of them on the board. Combining weights is chronologically the way in which the atomic theory was first introduced, first through Dalton's work, and this is the way most of us present the atomic theory. I'd like to add a category that I'll call modern techniques, and to characterize modern techniques, we'll consider briefly mass spectroscopy. And then finally, a third classification I'll mention is combining volumes of gases. Now, you realize this is not an all-inclusive list. These are only some of the ways we considered introducing the atomic theory, and I'll discuss only these. We decided we should not be slavish to chronology, but rather to logic. We decided that when it was more important to have a logical development, that we need not follow a chronological development. Now, combining weights lead to the atomic theory through a logic that to you and to me is absolutely irresistible. It's crystal clear. But we all know that to a student who is low in mathematical aptitude, it's a very confusing business. And he's not helped a bit by the story that it took Dalton's compatriots and peers some 50 years to understand this logic, and you have 3 periods in which to do it. The fact is that's a difficult way to introduce the student to the atomic theory. Modern methods. Why don't we introduce the student to atomic theory through a mass spectrometer? Well, a mass spectrometer is a large black box that the student really doesn't understand. In the first place, its explanation is circular. If you start discussing electrons bombarding the particles so they can follow a curved path, you have to assume the existence of particles in order to continue the discussion. So that's not really a very clear-cut logic when you come right down to it. Combining volumes represents a logic that is experimentally accessible and has direct significance to the student. 1 volume of hydrogen reacts with 1 volume of chlorine to provide 2 volumes of HCl. This logic of 1 unit plus 1 unit giving 2 immediately suggests portions or units and leads directly to a particulate view of matter. So we decided that the atomic theory was best introduced by providing experimental evidence of the combining volumes type, and then giving the student the opportunity to try to draw from that experimental evidence the Avogadro hypothesis. So we're going to show you the film, Gases and How They Combine, which presents a vicarious laboratory experiment in which several combining volumes experiments are portrayed. Then the film actually has an interruption, during which the students are given the opportunity to consider for themselves the significance of these experiments. Then, whether the teacher is able to evoke from the class discussion the Avogadro hypothesis or not, he can show the remainder of the film and let the students compare their conclusions of the significance of this evidence to the logic by which we derive the atomic theory from the combining volumes data. You can see that this film provides quite a natural introduction to the atomic theory. Notice also that it provides a natural introduction to the balancing of chemical equations, and that's the next subject taken up in the Chem Study course. At this point, we attempt to place in the student's hands, if possible, chemical models. If they're not available for all of the students, then have them available in the teacher's hands. But if possible, have them available on the desk at the time you introduce the subject of balancing equations. Notice how easy it is intuitively for the student to grasp the idea in terms of models in the atomic picture, that 1 molecule of O2 with 2 atoms will form then 2 molecules of water, 2 atoms of oxygen, 2 atoms of oxygen. Furthermore, the continuation of the balancing leads easily to the idea that 4 hydrogen atoms will be needed in these 2 molecules of water, and consequently 4 hydrogen atoms in H2. It will require 2 molecules of H2 to react with 1 molecule of oxygen to produce 2 molecules of water. Another idea that is intuitively easy to put across to the student is that different atoms will have different weights, and consequently we can proceed from the balanced chemical equation to weight relationships. Instead of weight relationships leading to the atomic theory and balancing equations, we draw the atomic theory from combining volumes and then proceed to deduce weight relationships in a very natural and easy way. This introduction to the balancing of equations led us to decide that the mole should be introduced as a number, if you like, a chemist's dozen, a means of counting atoms, because the balancing of equations and the deduction of weight relationships all comes from the atomic theory of nature. Consequently, we introduce the mole as a number, the chemist's dozen, instead of the more traditional weight-derived definition. And we find that it's no difficulty at all later on, if the student continues in chemistry, making a more rigorous definition. One final assurance you may wish is that with this introduction to the atomic theory, to balancing equations, weight relationships, and so on, that the student will end up with the facility that you're used to in the balancing of equations, weight relationships, and even in such a matter as the naming of compounds. In order to be sure that this happened, we have programmed deliberately throughout the course weight problems. They come up in every single chapter of the course. We find that even though a student may not, after Chapter 3, have the facility in weight problems that you would like and that you're used to, that by the time the course is over, he has this facility. And nowhere has he been stopped and presented with a mathematical obstacle in terms of balancing equations and deriving weight problems. Another systematic introduction was the formulas. We decided that we did not wish to confront the student with a long list of formulas to memorize. Consequently, we introduce a few in each chapter, and in each chapter we reinforce the relationship between the name and the symbol. Our experience is that at the end of the Chem Study course, the student has the facility in weight relationships, balancing equation, and use of names that we're used to.